Hey everyone, I am Miss Hu, your physics teacher. In this video, we will learn about the Hubble constant, calculating the receding velocity of a galaxy, and estimating the age of the universe. Yes, everything is measurable, even the universe. Well, actually not really, but physicists, they try to measure everything. So in this video, we'll be going through the equations, what we can measure, and how we measure them. Now, this video is designed for students who are taking the Physics IGCSE examinations, so we'll only cover the topics you need to know to answer the questions in those examinations. So first of all, let's learn about how we can measure galactic distance. That means the distance between the celestial bodies in the universe. So if we want to measure the distance of a galaxy from Earth, we can do so by observing the brightness of a supernova in that galaxy, usually type 1a supernova. Why? Because all type 1a supernova reach nearly the same brightness at the peak of their outbursts. They then follow a distinct curve as they decrease in brightness, so when astronomers observe a type 1a supernova, they can determine the approximate distance of the galaxy by comparing the apparent magnitude against the absolute magnitude of the brightness of that supernova. So for Physics IGCSE, we don't need to be able to actually calculate that distance, we just need to know how we can measure and calculate that distance. Now, if we want to measure the speed instead, and by now you should know about the concept of redshifting. If you don't know what redshifting is, please watch my other videos on Doppler and redshifting, as well as redshifting and how it is proof of the Big Bang Theory. Links are in the description below. Now, the redshifting of observed light from a distant galaxy, as you should know by now, is evidence that the galaxy is moving away from us. The difference in wavelength of the light due to the redshift can be used to find the receding velocity of the object moving away from Earth. The term receding velocity here means the velocity of the object moving away from us. Now, to understand this relationship, we can recall the wave equation of v equals f lambda. So taking the frequency of the light to be constant, you can rewrite the formula as f equals v over lambda. So if v1 over lambda 1 equals v2 over lambda 2, when we rewrite this, we can get lambda 1 over lambda 2 equals v1 over v2. Now in this case, lambda refers to the difference between the actual wavelength and the observed wavelength. So that means there is a difference due to the movement. That's why the matching speed would be the speed of the galaxy. Lambda 2 would be associated with the laboratory reference, which is of light, so the actual wavelength of the light that we should expect to see. And because of that, v2 is the speed of light of the laboratory reference. Good news is you will not be required to use this formula, so you don't have to memorize it. So I'm going to put a green cross here just to indicate you are not expected to be able to use this equation. You just need to know that we can measure the galactic speed based on the difference in wavelength due to the redshift. Whew, don't have to do the calculation. We went through this anyway because you are required to know this. You just don't need to use this equation. So now let's go into what you are expected to be able to apply. So now let's go into Hubble's discovery. So who's Hubble? So Hubble is Edwin Hubble, an astronomer who in 1929 found evidence that the universe was expanding by observing that the absorption line spectra from the light of distant galaxies have shifted towards the red end of the spectrum, and this phenomenon is known as redshift. He found that the light from more distant galaxies were more redshifted than the light from nearer galaxies, as we can see in this sample. So the lab reference is the actual absorption spectrum of a particular light that we are expecting to see, and the further away the star or galaxy is from us, the more these bands have shifted towards the red end of the spectrum. So what this suggests is that galaxies which are further away from the Earth are moving faster than the galaxies which are closer. The proof of redshifting with moving galaxies is all covered in my video about redshifting. So now let's move on to Hubble constant. So from this relationship, a graph was obtained showing the relationship between the recessional velocity and distance of galaxies. So as you can see in this graph, where the recessional velocity is on the y-axis and distance is on the x-axis, The trend of the plots show a linear graph. And from this, Hubble's law was formed, which states that the recessional velocity of a galaxy is proportional to its distance from Earth as shown in the graph. This can be expressed as an equation of h0 equals v over d, where h0 is the Hubble constant, v is the recessional velocity, which is the velocity of an object moving away from Earth, and d is the distance between object and the Earth. Because recessional velocity has a unit of meters per second, and distance has a unit of meters, so when you cut off the unit of meters, you're left with the unit per second, which is why Hubble constant is expressed in the unit per second. Hubble constant is defined as the ratio of the speed at which the galaxy is moving away from the Earth to its distance from the Earth. And this constant, as you can see, is just based on the equation. The current value of the Hubble constant is stated as 2.2 times 10 to the power of negative 18 per second. And yes, you are required to know this value for Physics IGCSE. The good news is that because this topic is so new, students are generally not required to memorize this number, so this value is usually provided in your exam. So the important thing is for you to recognize the number. So when you look at it, you know, oh, that's a Hubble constant, even if you don't have the number committed to your memory. At least recognize it so you see it, you know, this is the Hubble constant. So why I've written it here as the current value is because the Hubble constant value does change as the universe ages. The Hubble constant decreases with time, but the decrease in value will take millions, if not billions of years. So for now, it is constant at 2.2 times 10 to the power negative 18 per second, and that's all you need to know. So if we take a closer look at this graph, we'll find that this graph is able to give us a lot more information than just Hubble constant. You see, when the distance is 0, this means that all matter in the universe is at the same point because d is 0, right? So there's no distance, there's no space between all those objects. So what this means is that at distance 0, this is when the Big Bang occurred. Now, based on the equation where the Hubble constant is equal to the recessional velocity over distance, or h0 equals v over d in symbols, we can see from the graph that the gradient of the graph is the Hubble constant. We also know that the unit of the gradient, which is the Hubble constant, is per second. So if we take the reciprocal, which means 1 over h0, this makes the unit become seconds. So the reciprocal here means 1 over h0. So if the unit was per second, you flip it, it becomes seconds. That's what this sentence means. Because the units of the reciprocal is seconds, this tells us that the reciprocal of the gradient is time, which in this case represents the amount of time the universe has been expanding. So based on this, the astronomers have estimated the age of the universe to be about 13.7 billion years. Now, you are also expected to know the age of the universe, and yes, this has come up before in a past year question. What if you can't memorize it? Well, you're not expected to. In fact, the past year question asked students to calculate the age of the universe. So to calculate this, all you need to do is just take the reciprocal of the Hubble constant. So given that the Hubble constant is 2.2 times 10 to the power negative 18 per second, we can calculate the age of the universe this way. So how do we calculate the age of the universe? So I'm going to show you the working. Given that the Hubble constant is this value of 2.2 times 10 to the power negative 18 per second, we can write it this way. The age of the universe is equal to the reciprocal of the Hubble constant. So you're not required to memorize the Hubble constant, but you are required to know this relationship. So you must know age of the universe is 1 over h0. Then all you do is substitute the value of the Hubble constant in the equation. 2.2 times 10 to the power of negative 18. Now using your calculator, this is the value you would get. 4.55 times 10 to the power of 17. So because the Hubble constant unit is per second, this gives us the value in seconds. But usually, we wouldn't be expressing the age of the universe in seconds. It's possible, but difficult to comprehend. We would normally express this in terms of Earth years. So let's convert this time into years. Now, how do we do that? Remember that one Earth year has 365 days, one Earth day has 24 hours, 1 hour has 60 minutes, and 1 minute has 60 seconds. So when we calculate this out, you would end up getting 1.44 times 10 to the power of 10 years. And that's how you estimate the age of the universe. So yes, this value is slightly different from the value that was written on the previous slide of 13.7 billion years, but you have to remember this is merely an estimate because a lot of things have changed as the universe ages. For example, the number of hours in one Earth day, that means the time it takes for Earth to make one full rotation around its axis, is actually different. It is actually longer now compared to millions of years ago. The same also applies for the orbital duration of the Earth around the Sun. And that's why even for these kind of calculations, a lot of adjustments have to be made to get a more accurate number. For physics IGCSE students, you don't need to know that estimation, you just need to know how to get this number, and you'll be marked correct as long as you know how to use the Hubble constant correctly to calculate the age of the universe. And that is it for this video. So if you found this video to be educational and helpful, please click like and subscribe for more physics lessons from your physics teacher, Miss Ho. Do help me keep making free educational video lessons and lab practicals. Donations are welcomed at my Ko-fi page. That's ko-fi.com/physicsrocks. If you would like access to notes, quizzes, and syllabus updates, please visit my website at physicsrocks.com. Happy studying!